Near the surface, octopuses are clever, muscular hunters that almost feel relatable. But as you descend into the ocean's depths, their bodies become softer, stranger, and almost unrecognizable, arms stretching to grotesque lengths, eyes warping or vanishing, and flesh turning translucent. Why do the animals we know so well mutate into such unsettling forms below the waves? The real answer is not just eerie, it reveals how life can be reshaped by darkness, pressure, and isolation in ways we are only beginning to understand. And it all starts with the octopus you thought you knew. In shallow coastal waters, the octopus is built for action. Take Octopus vulgaris, the classic example. Its arms are thick with muscle, each one packed with thousands of powerful fibers. These arms aren't just for crawling. They can twist, squeeze, and even pry open the toughest shells. Underneath the skin, chromatophores, tiny pigment cells, expand and contract in a flash, shifting the octopus's color and pattern in less than a second. This is camouflage at its highest level. A rock, a patch of algae, a ripple of sand, an octopus can mimic them all, blending into its surroundings so completely that even sharp-eyed predators pass by without a second glance. The secret is control. Muscles in the arms and mantle let these animals dart across reefs, wedge themselves into crevices, or launch a jet of water for a quick escape. Their skin is a living display, constantly updating to match the light and texture of the world above. In the words of cephalopod expert Roger Hanlon, octopus arms respond to stimuli even an hour after amputation, showcasing decentralized intelligence. The brain delegates, but the arms think for themselves. None of this comes cheap. All that muscle and rapid-fire camouflage require energy, and a lot of it. In the well-lit, food-rich shallows, that is not a problem. Prey is everywhere. The octopus can afford to be a sprinter, a shapeshifter, and a master of disguise. But these same strengths become burdens as soon as light fades and food grows scarce. What makes the shallow water octopus so impressive here will soon turn into a liability in the deep. Shallow octopuses thrive in the epipelagic zone, less than 200 meters down, where sunlight pours through clear water and the reef is a maze of hiding places. Here, Octopus vulgaris and its relatives hunt with purpose. They stalk crabs, shrimp, and small fish, using both patience and speed. A favorite tactic is to creep along the ocean floor, arms spread wide, tasting and feeling with specialized suckers that can detect chemicals left by prey. When the moment is right, they strike fast, wrapping their arms around a meal and pulling it back to their den. Dens are more than just shelter. Each octopus selects a home, a crack in the rocks, a discarded shell, or an abandoned burrow. They line the entrance with rocks and shells, sometimes stacking them as a barricade. This den becomes a headquarters for hunting, resting, and laying eggs. Some octopuses have even been seen collecting coconut shells or bottle caps, using them as portable armor or tools, a rare example of tool use among invertebrates. In these sunlit shallows, camouflage is an everyday skill. The octopus's skin can shift color and texture to match coral, sand, or algae. This ability is not just for defense, it makes them invisible to both predators and prey. The vibrant, ever-changing world of the reef gives them everything they need: abundant food, places to hide, and enough light to see and be seen. All these advantages let shallow octopuses live as active hunters, problem solvers, and masters of disguise. But every trait that helps them here, strong muscles, quick reflexes, and a hunger for action, relies on a world full of light, shelter, and food. Take those away, and the rules of survival begin to change. At a depth of nearly 1,200 meters, the ocean is a world without sunlight, where the boundaries between animal and environment begin to dissolve. It is here that remote-operated vehicles, guided by pilots who spend months at sea for moments like this, sometimes catch sight of something that does not seem quite real. The glass octopus, Vitriolidinella richardi, floats into the lights of a remote-operated vehicle, and for a moment even the most seasoned pilot falls silent. Through the lens, the animal appears almost invisible. Its skin is so transparent that the organs inside, intestines, optic nerves, even the shimmering outline of its digestive tract, are laid bare, There is no color, no pattern, no attempt to hide in the usual sense. Instead, the entire body is a living window, blurring the line between creature and water. A pilot's voice crackles over the control room speakers, half whisper, half awe. It sounds like seeing a ghost. You can watch its heart beating. The remote-operated vehicle hovers, zooming in. Every pulse and contraction is visible, the rhythm of life on display in the open water. The arms, long and fine as threads, drift behind the body, almost disappearing into the darkness. Only the eyes break the illusion, large, silvery, and unblinking, staring out from a head that is little more than a clear balloon. This is not transparency for spectacle. In the mesopelagic zone, where there is nowhere to hide and predators hunt by silhouette, being see-through is the best defense. The glass octopus body is so thin and soft that it barely casts a shadow. With no pigment, no muscle bulk, and almost no visible outline, it becomes a phantom, slipping through the water unnoticed. Even the digestive gland, usually a giveaway, is tucked away as a narrow rod, minimizing its profile. For researchers, catching this on camera is a rare victory. The footage from July 2021, recorded by the Schmidt Ocean Institute remote-operated vehicle Sebastian, changed how scientists understood deep-sea camouflage. The pilot's reaction, equal parts disbelief and excitement, echoes the experience of anyone seeing this animal for the first time. It is not just an octopus, it is a living secret, shaped by a world where light is a memory and survival means erasing yourself from view. The glass octopus is proof that in the deep the rules of life are rewritten, sometimes in ways that leave even the experts speechless. Transparency is one of the most effective tricks in the mesopelagic zone, a region stretching from about 200 to 1,000 meters below the surface. Here, sunlight fades to a dim blue haze, too weak for photosynthesis but still strong enough to betray the outline of anything solid. Predators hunt by looking up, scanning for silhouettes against the last traces of daylight. In this world, color and pattern are liabilities. The safest body plan is one that lets light pass straight through. The glass octopus is the master of this approach. Its tissues contain so little pigment that most of its body appears invisible, except for the eyes and a slender digestive gland. Even these organs are arranged to minimize their shadow, flattened, tucked away, or aligned vertically to present the smallest possible target. The skin is thin and delicate, lacking the muscular chromatophores that enable rapid color change in shallow species. Instead, the glass octopus relies on its own absence, turning the challenge of hiding in open water into an art form. The reason for this radical design lies in the physics of light itself. In the mesopelagic, water absorbs and scatters sunlight, leaving only a narrow band of blue wavelengths. Anything with pigment or dense tissue will cast a shadow or block this faint light, making it easy prey for sharp-eyed hunters like squid, fish, or even other octopuses. But a transparent body lets light pass through, erasing the outline that would otherwise give an animal away. Experiments with artificial models have shown that predators in this zone are far less likely to attack objects that transmit light, even if they can see the faintest trace of organs inside. Transparency is not perfect. Some light still bends or scatters at the edges, and the eyes remain a weak point. But in a place where the background is always changing and there are no rocks or reefs to hide behind, it is the closest thing to invisibility. The glass octopus's entire anatomy is shaped by this pressure. Soft, gelatinous tissue instead of muscle, organs reduced or repositioned, arms stretched thin and trailing behind to avoid casting a shadow. Every feature is a response to the relentless searchlight of the deep. In the twilight zone, survival is measured in shadows. Here, the best defense is not to outswim a predator or outsmart it with camouflage. It is to disappear entirely, blending into the water itself. The glass octopus is proof that even in the deep, the rules of life are written by the play of light and the need to remain unseen. Deep below the sunlit shallows, muscle becomes a luxury few octopuses can afford. In the ocean's upper layers, every movement, jetting, crawling, even a quick color change, burns through calories at a staggering rate. Each thick arm and powerful mantle muscle is a metabolic engine demanding a steady flow of oxygen and food. But as daylight fades and prey grows scarce, the cost of staying muscular rises with every meter descended. In these dim zones, energy is a currency measured in survival, and extravagance is punished swiftly. The shift is not just about losing bulk, it is a total reworking of what it means to be an octopus. Dense muscle fibers are replaced by tissues that are soft, watery, and flexible. The body takes on a gelatinous consistency, more like jelly than flesh. This is not weakness, it is strategy. Muscle tissue is expensive to maintain, it needs constant fuel, and in the deep, fuel is in short supply. By letting go of heavy muscle, octopuses lower their metabolic rate, allowing them to drift for hours, even days, without eating. The numbers are stark. A shallow water octopus may consume up to 30% of its body weight in food each week, just to power its active lifestyle. In contrast, deep-sea species survive on a fraction of that intake, sometimes going weeks between meals. Their tissues hold more water and less protein, reducing density and helping them hover in the water column without sinking or swimming. This shift is not just about saving energy, it is about making every calorie count. Where a shallow octopus burns bright and fast, its deep cousins are built for endurance, not speed. Even respiration changes. With less muscle to feed, oxygen demand drops. The gills and skin can absorb enough to keep the animal alive, even in low oxygen water. Every adaptation, from the texture of their skin to the chemistry of their blood, is tuned for efficiency. In a world where food is rare and movement is costly, muscle becomes a liability. The deep ocean favors those who can do more with less, and the octopus answers by letting its body soften, slow, and fade into the background. Floating in the deep ocean is not a matter of luck. It is a feat of chemistry and physics, written into the bodies of octopuses that abandon muscle for something far stranger. Instead of relying on powerful arms or dense tissue, these animals become almost weightless, their bodies tuned to match the density of the water that surrounds them. This is how they drift, neither sinking nor rising, maintaining what scientists call neutral buoyancy. In shallow waters, octopuses stay grounded by choice. Their muscles are heavy, and their bodies are built for crawling, gripping, and jetting away from danger. But deep-sea species trade all that away. Their tissues absorb more water and shed protein, turning soft and gelatinous. The result is a body that is barely heavier than the seawater itself. There are no gas-filled chambers, no air pockets to keep them afloat. Instead, the secret is in the composition of their flesh, high water content, low density, and an almost eerie softness that lets them hover with no effort at all. Some cephalopods, like certain squid, use chemical tricks, storing ammonium ions in their tissues to lighten their load. For octopuses, the evidence points toward a simpler solution: make the body as watery and light as possible. The difference is subtle but profound. By letting go of muscle and packing their cells with water, deep-sea octopuses become creatures that float by default. They do not need to swim constantly to stay suspended. They simply exist in a slow-motion drift, conserving every bit of energy for when it is truly needed. This adaptation is more than a curiosity. In a world where food is scarce and movement is costly, floating is survival. The octopus's body becomes less a tool for action and more a vessel for endurance. It is a quiet mastery of chemistry, a way to beat gravity, pressure, and hunger all at once. Here, in the deep, the rules of life are rewritten at the molecular level. The result is an octopus that drifts, patient and nearly invisible, waiting for the next challenge the darkness will bring. At 1,397 meters below the surface, in the cold darkness of Monterey Canyon, a female granellodon octopus began a vigil that would outlast any other known in the animal kingdom. In May 2007, researchers from the Monterey Bay Aquarium Research Institute first spotted her clinging to a rocky outcrop, arms curled protectively around a small cluster of EGS. The water temperature hovered just above freezing, and the pressure at this depth was enough to crush a submarine hull. Yet month after month, the same octopus remained, never straying, never feeding, her body growing paler and thinner with each passing season. The team returned again and again, piloting their remotely operated vehicle down to the same spot. Each time there she was, motionless, except for the gentle wave of her arms as she groomed the eggs, keeping them free of silt and parasites. The researchers watched as the months stretched into years. By the second year, her skin had lost its color, her mantle had shrunk, and her eyes seemed sunken with exhaustion. She never left her post, not even once, for food or rest. Every ounce of energy she had was spent keeping her eggs safe in the freezing dark. 53 months passed, over 4 years, before the eggs finally hatched. This is the longest brooding period ever recorded for any animal, not just for octopuses or other cephalopods. Most octopuses live fast and die young, their entire lives compressed into a year or two. But in the deep, cold water, everything slows down. The low temperatures drag out the metabolism of both mother and embryos. Development that would take weeks in warm, shallow seas stretches into years. The mother survives by lowering her heart rate, moving as little as possible, and burning her own body for fuel. By the time the last hatchling drifted free, she was little more than a husk, her life spent entirely on a single act of parental care. This extraordinary sacrifice is not an accident of nature. It is a direct answer to the deep sea's harsh rules. Food is so scarce that the only way to guarantee survival for the next generation is to protect them at any cost, for as long as it takes. The Granellodon's vigil is a story written in slow motion, shaped by cold, pressure, and the relentless passage of time. It is a reminder that in the abyss, survival is not just about strange bodies and eerie shapes. It is about the patience to wait out the darkness no matter how long it lasts. The deep ocean is a world where light is less a presence and more a memory. For octopuses, the loss of sunlight brings a new kind of pressure, one that shapes not just their bodies but their senses. Nowhere is this more dramatic than in their eyes. In the twilight and midnight zones, vision becomes a gamble between survival and starvation. Some octopuses respond by making their eyes enormous, stretching them to the edge of what their bodies can support. Others go the opposite way, letting their eyes shrink or disappear entirely, surrendering sight to the darkness. Stephen Haddock, a leading researcher at the Monterey Bay Aquarium Research Institute, has spent decades studying how faint glimmers of bioluminescence drive these changes. According to Haddock, the midwater is filled with brief, silent flashes, tiny explosions of blue-green light from jellyfish, shrimp, or other cephalopods. For an octopus drifting at 800 meters, seeing these flashes can mean the difference between finding a meal and starving. That is why species like Japatella diaphana grow eyes that are nearly 3/4 the length of their entire mantle when they are young, maximizing every photon. The glass octopus, Vitrilodonella richardi, has eyes that seem almost too large for its transparent head. These eyes are packed with photoreceptors tuned to the blue wavelengths that travel farthest through seawater, allowing the octopus to spot the faintest glimmer from a distant glowing prey item. But as you descend further, even bioluminescence fades. At 3,000 meters and beyond, the cost of maintaining large eyes outweighs the benefit. Here, octopuses like Grimpeteuthis, the Dumbo octopus, let their eyes regress. Some have tiny, pinhole-sized organs buried deep in their heads. Others show only remnants with retinas so thin they can barely distinguish light from dark. Instead of vision, these octopuses rely on touch and chemical cues, using the sensitive suckers on their arms to explore their world. The energy saved by reducing eye size is diverted to endurance, helping them survive on the bare minimum in a world where food drifts down like snow and every movement must be justified. The split between eye enlargement and reduction is not random. It is a direct answer to the changing rules of the deep. Where bioluminescent flashes are common, large eyes rule. Where darkness is absolute, eyes become an afterthought. Haddock sums it up simply. Bioluminescence selects for big eyes in the midwater, but deeper down vision yields to touch. This divergence is more than just a curiosity. It is a window into how life bends to the most extreme environments on Earth. In the deep, survival is not about seeing everything. It is about seeing just enough or letting go of sight altogether. For octopuses, the eyes tell the story of where they live, what they hunt, and how they endure in a world that seems designed to erase them from view. At nearly 7,000 meters below the surface, the Dumbo octopus drifts through a world of pressure and cold that would destroy most living things. Its anatomy is a catalog of deep-sea solutions, each trait a quiet answer to the violence of the abyss. There is no ink sac here. In total darkness, ink would be useless, and carrying the extra weight would only waste energy. Instead, the Dumbo octopus is built for efficiency. Its arms are joined by a web of translucent skin, forming a loose, umbrella-like skirt. When the animal swims, this web unfurls, catching water and letting the octopus glide with almost no effort. The arms themselves are long and delicate, trailing behind or curling inward, never flexed for a sudden grab. Muscles are soft and gelatinous, not for strength, but for survival under crushing pressure. The body is so watery that it nearly matches the density of the surrounding seawater, allowing the Dumbo to hover above the seafloor without sinking or floating away. Instead of jetting like its shallow cousins, the Dumbo octopus moves by flapping a pair of fins that look like ears on either side of its mantle. Each slow beat pushes the animal forward or upward, or in lazy circles, no sudden bursts, no wasteful sprints. The fins are powered by just enough muscle to keep the animal moving, but not enough to burn through precious calories. This is locomotion designed for endurance, not speed. Michael Vecchione, a cephalopod specialist with NOAA and the Smithsonian, has spent years studying these deep sea forms. When NOAA's Okeanos Explorer captured footage of a Dumbo octopus hovering at 6,957 meters, Vecchione's team pored over every frame, counting the number of fins and measuring the webbing between the arms. They confirmed what few had dared to guess. This was the deepest living octopus ever recorded. Vecchione points out that, at these depths, even the smallest anatomical detail matters. The webbed arms, the weak muscles, the absence of ink, all are clues to how this animal survives where nearly nothing else can. The Dumbo octopus has abandoned the classic octopus playbook. There is no crawling across the rocks, no squeezing into crevices, no display of colors. Its skin is pale and featureless, lacking the chromatophores that let shallow species vanish against the reef. Here, camouflage is not about blending in, but about being so soft and so light that the animal becomes part of the water itself. The beak is small and weak, just enough to swallow tiny crustaceans and worms whole. The digestive system is slow, built to extract every possible calorie from whatever drifts down from above. Every feature of the Dumbo octopus is a convergent solution to the same problem: how to exist in a world defined by scarcity and pressure. The webbed arms and fins are not unique to this species. Other deep-sea octopuses have evolved similar traits, but nowhere else do they come together so completely. The result is an animal that looks like it belongs to another planet, but is in fact the endpoint of millions of years of adaptation to the most extreme environment on Earth. Vecchione says it best: "We see only glimpses, but every glimpse tells us that the deep ocean is not empty. It is just waiting for us to look closer." Every now and then, a deep-sea octopus drifts into the lights of a submersible, and for a few minutes the world gets a glimpse of something almost mythic. But those glimpses are all science has to work with. After decades of exploration, the most basic facts about these animals remain out of reach. No one has ever seen a Dumbo octopus mate. No one knows how long they live or how many exist in the abyss. The deepest living species, Octopuses, has been filmed at nearly 7,000 meters, but only ever as a solitary wanderer, never in pairs, never with eggs, never with young. Louise Alcock, a leading deep-sea cephalopod ecologist, has spent her career cataloging these mysteries. She puts it plainly: abyssal reproduction is still unobserved because we simply can't sample enough or for long enough to catch it happening. The ocean at these depths is so vast, so difficult to access, that even the most advanced remotely operated vehicles can only linger for a few hours at a time. Every sighting is a chance event. By the time the cameras are ready, the octopus may already be gone, fading back into darkness. The gaps are everywhere. No one has ever documented Dumbo octopus courtship or watched a female lay her eggs. No one has tracked a single individual from birth to death. Lifespan estimates are guesses drawn from the slow metabolism imposed by near-freezing temperatures and the sluggish pace of life. The only clues come from the bodies themselves, a lack of scars or injuries, the slow wear of tissue, the rare sight of a female with eggs. Unlike their shallow relatives, which can be bred and studied in aquariums, deep-sea octopuses collapse and die when brought to the surface. Their bodies, built for crushing pressure, cannot survive even a brief ascent. Even basic feeding is a puzzle. The Dumbo octopus swallows prey whole, tiny worms, crustaceans, and whatever particles drift down from above. There is no tearing, no display of strength, only a gentle engulfing. This is not the behavior of a hunter, but of a survivor, conserving every calorie. Scientists have only confirmed this by analyzing the contents of preserved specimens or by watching a few lucky moments captured on remotely operated vehicle footage. The rest is silence. What little is known has been pieced together from fleeting encounters and indirect evidence. Population size, breeding cycles, and even the full range of species diversity remain hidden. The deep sea keeps its secrets well. Each new dive might bring a breakthrough, but more often it brings only more questions. Alcock and her colleagues return from expeditions with hours of video and only a handful of answers. The ocean, it seems, is patient. It yields its stories slowly, if at all. The real frontier is not just the animals themselves, but the limits of what humans can observe. The deeper we go, the more the octopus becomes a symbol, not just of adaptation, but of the mystery that still rules the abyss. For every trait that can be explained, there are a dozen that remain unknown. In the words of Alcock, we know almost nothing, and that's what makes it so compelling. The deeper the octopus, the deeper the mystery. The ocean's depths hold life so radically adapted that it challenges our sense of what's possible and what's waiting unseen. As submersibles reveal new species each year, scientists estimate up to 2/3 of deep-sea animals remain undiscovered. The unknown isn't just beneath us, it's evolving in real time. Every glimpse into the abyss reminds us, Earth's strangest mysteries are not behind us, they are unfolding far below, right now. What do you think lies in the dark, still undiscovered?